for inviting me to this summer school. So I'm going to discuss it's not a classical topic in mathematical finance. It's something new we have been working on with my colleagues Ananova and RenYuan in Oxford. And I'm very excited about it. So I hope I'll be able to share some of our interest with you and get you curious to learn more about this topic. So we call this excursion risk, but it's really what we think is a useful new approach to the analysis of dynamic trading strategies. And it links to a classical topic in probability theory, which is the theory of excursions. So what I will try to do in these lectures is first tell you why this is an interesting viewpoint for applications in finance, then link it to the theory of excursions, and then give a little bit overview of the key results of that theory, which will be useful for us, and then derive some, use that theory to derive some results for applications to trading strategies in finance. So that's the overview of this of these lectures. So, oops, yeah. Okay, so can you see the outline?
Yes.
Okay,
yes.
So this is a overview of what I'm going to cover. So I entitled this Excursions in Mathematical Finance. So today I'm going to discuss the background, the motivation. Why are we talking about excursions? What kind of trading strategies are we interested in, and so on? And show you the link between trading strategies and excursion. The link is really not obvious from the beginning, and maybe that's why people haven't used this powerful theory in finance until now. And I'll show you that a large class of trading strategies may be represented through excursions of a stochastic process, and this leads to a useful way for scenario analysis of these trading strategies. And then we will have two types of results in this theory. The first type of result is what I call pathwise results. So in the first half of the lecture, so lectures 1 and 2, we will make absolutely no assumptions on any stochastic process, the price, no assumptions at all on anything. And we will derive results which will hold along every price path. And this is what I call scenario analysis. So give me any scenario, and I will use this approach to tell you something about the behavior of trading strategies along this scenario. And this will be today and tomorrow. And then in the second part of the talk, we will make probabilistic assumptions on prices and trading signals. More specifically, if we make the assumption that they're given by Markov processes, then we will show that, Ito's excursion theory, a powerful theory developed by Ito in the 70s, it can be used to derive many, many results and many interesting, tools for analyzing these trading strategies in terms of excursions of some underlying Markov process. And at the end, I will try to use this approach to build new models, which instead of analyzing trading strategies in existing models, I will suggest that, how this theory can be used to build new classes of models, which are, we think, more adapted to the analysis of these applications. And I will outline some parametric and non-parametric constructions there, which lead to new classes of stochastic processes, which remain to be studied in more detail. So a lot of open questions will be discussed in the last part. Okay, so that's the overview. So now let's jump into the topic, which is so the first part, I will discuss trading strategies and what I call trading signals, and then how they link to what we call excursions. Okay, so what are we talking about? It's a little bit mysterious, I acknowledge. So I'm going to try to explain first what even the title of these talks mean. So, so the starting point of this study is the following remark, that many different trading strategies can be summarized in the following way. You have some traded asset, so it can be a portfolio, it can be a single asset. So let's call the price of this asset PT at time t. And then the basis of the trading strategy is that you have a valuation for that asset, which we call AT. It's a target value. So this can be, for example, the result of the analysis of a financial analyst. They say, this stock is trading at 200, but I think it's really worth 250. So it can be a qualitative assessment, doesn't have to be a formula-based assessment. Or it can be the result of a statistical forecast. So you can have statistical arbitrage strategies. They forecast with various methods the value of a portfolio. So this gives you another way to arrive at a target value. But for our purposes, we don't really care how you arrive at the target value. There is a target value, there's a price. And so what you look at is the difference between the target value and the price. And we will call this a trading signal. So if this signal is non-zero, it means there's something interesting to do. If the signal is negative, so sufficiently negative so that you consider it statistically significant, then it means that your asset is undervalued. So this means it's a buying opportunity. If this signal is sufficiently positive to be statistically significant again, then it means it's an opportunity to short the asset because it's overvalued. So that's the idea. And I would say 99% of trading strategies people use are of this type. There is a price, there is some assessment of the price by the trader, and then they compare the two. Okay. So examples where, first example is when the forecast or the assessment is a qualitative assessment. So fundamental strategies are of this type. So you have an analyst who arrives at some fundamental value for a stock. They think that the stock is worth 80 because of the balance sheet of the company and their forecast for the earnings and so on. And so they compare the current market price to this fundamental value. So that's a very commonly used approach. And then there are statistical approaches to arrive at a forecast. For example, one of the examples I will give in the data examples is pairs trading. So you take two stocks with prices P1 and P2, and for example, Coca-Cola, Pepsi-Cola, you think that the prices are going to be related because they are affected by the same risk factors. So you think if one goes up, the other one should go up, and so on. And so you look for a combination of these stocks, which means a portfolio, long-short portfolio, which is supposed to be stationary. So in the long term, you think that this portfolio, this combination should be around zero, because the two stocks cannot move away from each other indefinitely. So this difference or combination cannot go away from zero too much. So this implies that it has to have some mean reverting behavior. And so if you can estimate the mean in some way, for example, by looking at the long-term average of this combination, then it means that the mean can be a forecast of the long-term behavior. So then this is the principle behind pairs trading. You find a combination which is supposed to oscillate around zero, and then you bet on the fact that it's going to come back to zero periodically. Now, a generalization of this idea is the more general form of statistical arbitrage strategies. So you don't need to necessarily do this for two stocks. You can say, okay, well, you know, I have a collection of assets which are somehow very correlated. They're in the same sector, or they're bonds from the same issuer, or something like that. They are very correlated. So I look for stationary linear combinations of these prices. So I look for a linear combination or a portfolio of these assets, which has stationary behavior. So then stationary means that if I can estimate its long-term average, it should somehow oscillate along this level A. And so if it's above A, it means that it should go down to A. If it's below A, it should go up to A. So this gives me a way to forecast the direction of the movement of this portfolio. And this is based on the statistical idea of called co-integration. So co-integration was introduced by Engel and Granger in 1987. It's the idea that you can have non-stationary processes. Typically, prices are non-stationary, but they can have a stationary linear combination, typically with positive and negative coefficients. And so this has implications in terms of trading. So if you couldn't find that stationary linear combination, then this linear combination will have mean reverting behavior. So it's forecastable over some horizon. Okay, so these are examples how of strategies which are very, very well known and used a lot of, and they all are of the type I described before. It's they all have a reference price and then a target value, and then you trade based on the difference between the two. Okay. So what's important is that independently of how you construct the forecast, in these three examples, forecasts are constructed in different ways. In one way, it's qualitative. The other way is it's statistical. Once you construct the forecast, then you don't really care about the origin of the forecast. Then from that point onwards, the strategies all proceed in the same way. You look at the difference between the price and the forecast. That's we call the signal. And then you trade when the signal crosses a threshold. So typically 0. If the signal goes above 0 or below 0, that's where you want to change your position. Okay, so that's the fundamental remark I would like to start with. Now, let me give an example which is more explicit. So let's take one of these examples, pairs trading, which is a very well studied topic in quantitative finance. There are books about this, there are many papers about this, mostly practitioner papers. This is a very widely used strategy. So what is pairs trading? Well, the starting point is you identify pairs of assets. Sorry. So you identify pairs of assets which are supposed to be linked in some way structurally. And what we mean by linked is, in statistical terms, we mean that they're co-integrated. So co-integration is a concept introduced by Engel and Granger. As I mentioned, this is the reference here. It's very well known in econometrics. It means that there exists a linear combination of P1 and P2, which is stationary. That's the definition. Okay, so P1 and P2 do not need to be stationary. For example, think of some exponential Brownian motion or Black-Scholes model, but that's not stationary. But it means that these are two non-stationary processes which have a stationary combination. So of course, this is only possible if the coefficients are positive and negative. So typically, examples are stocks in the same sector or two bonds with different maturities with the same issuer. They have a reason to be close, follow each other. And so the idea is that they cannot go too far from each other. So there has to be some difference which is stationary and oscillates around 0. Okay, so now what this means is that there exists a linear combination, P1 minus WP2 with the coefficient W here, which needs to be estimated, which is either stationary if we strictly follow the definition, or in practice slowly varying, which means that it may not be stationary, but its distribution will change slowly over time. So over short time, like 1 day or 1 week, you can assume it's stationary over short times, and you have a good approximation there. So the idea proposed by Engel and Glager is that, well, in general, if you take two non-stationary processes and you regress one on the other, this is going to give you nonsense. But if the processes are co-integrated, then it's a valid regression. So if I take P1 and P2 and I regress P1 and P2, in general, if P1 and P2 are non-stationary, this doesn't make sense. I can find total nonsense if I do that. But if P1 and P2 are co-integrated, then there exists a coefficient W, which makes this regression well posed, and that's what we're looking for. And so this is so in practice, that's how you apply this theory. You take a candidate pair, you do the regression, you find some residual and coefficient, and if there is co-integration, then the residual is going to be a stationary process. So if you include here a constant, then this has mean zero. If you don't include a constant, this can have non-zero mean. But it's not an IID process in general. It's a stationary process, but it's not necessarily IID. So stationary means that it's going to have some mean reverting property. Otherwise, it's going to just go to infinity or minus infinity. So this is the idea of co-integration, again, very well known in econometrics and widely used in trading. Okay. So now what do you do with this? Okay, so I do the regression of P1 and P2. I find the coefficient W and the residuals. Now what? What do I do with this? Well, if there is indeed co-integration, then it means that the residual is supposed to be stationary. So I can estimate its mean using a moving average or something. So let's say I take the n previous dates and I use the n previous dates to estimate the sample mean. This is one way. You can do it in other ways. And I will call this sample mean A of tk, if I computed that day tk. And this is my trading, this is my forecast for the price of this portfolio P1 minus WP2, because that's the mean of this portfolio. And then if it's stationary, I expect that it's going to revert to this mean at some horizon. So then it means that in this case, so in price trading strategy, this is how it works. You estimate the mean of this difference, and then you say, well, the trading signal is the current value minus the mean. And so the current value is in fact the value of a portfolio. It's P1 minus WP2 minus the estimated mean. And well, if I think it's a stationary process, then it cannot always stay above or below its mean. It has to, if it's above, it has to go below. If it's below, it has to go above. So this means that this process S is going to mean revert to zero. Okay, so it's just a way of constructing a signal from prices which mean reverse to zero. And then from then on, it's exactly what I was saying. So if this signal is above zero, you expect it to go to zero. So then if you hold the position which gains from this forecast, then that's a good strategy. And if it's below zero, you expect it to go up to zero. So then you do the following thing. If the signal is positive, then you try to profit from the expected mean reversion to zero. So you want to short this portfolio P1 minus WP2. So you want to hold the portfolio minus 1W. So this is the first coordinate, is the position in asset 1. And the second coordinate is the position in asset 2. So this is exactly the opposite of this linear combination. And this portfolio will have that value minus S. And when S goes to zero, well, you will gain. And if S is negative, then you want to hold the opposite portfolio. So that's the idea. That's the idea in pairs trading. And of course, you can hold exactly this portfolio, or you can hold a multiple of this portfolio. It works in the same way. So how much do you want to invest in the portfolio? That's another decision, but it will always be collinear with this portfolio. Okay, so that's the idea behind pairs trading. So here's an example. I will give some example. We'll come back to these examples but tomorrow, and afterwards we'll analyze them more. So here's a typical example. You take two stocks in the sector, Coca-Cola, Pepsi-Cola. Anybody will guess that they have to be related, unless there's something funny going on. They will be affected by the same economic factors. So people expect that Coca and Pepsi will not go away from each other a lot. And so if you do, so in this example, we look at Coca Pepsi over intraday prices over a long period. I'm going to again come back to the detailed description of the data tomorrow. But so every day you do a regression of Coca and Pepsi on the previous day. You calculate the coefficient W, and then this is an example of one trading day. Time is in seconds. This is how it behaves in one trading day. So the signal I plot here is a linear combination of Coca and Pepsi. The linear combination which gives you the minimum variance. That's how you do the regression. And then you see this is the signal that I call ST. You can see that over one day, it goes up and comes down, and it will cross zero many times. So here are many zero crossings. Here again here, and so on. And so every time it changes sign, that's when you want to maybe rebalance your trade. So that's an example of pairs trade. Oops, so I should go opposite way. Okay. So here's another example. Again, I will show you more about this example tomorrow. So here are these are not stocks, these are exchange traded funds. So SH and SDS, so these are two exchange traded funds that are traded in the US market. They both are what's called short ETFs. They short stocks in the S&P 500, and they short similar portfolios, but not exactly the same. But as you can see from the graph on the left, so this is the result of the regression. You regress SH on SDS to find these coefficients, 9.64 plus 0.67 SDS. So it means that if you are long SH and you are short 0.67 shares of SDS for each share of SH, then you get the orange graph here, which shows that a certain linear combination of SDS will track very closely SH. So this is exactly what pairs trading tries to do. You try to find a linear combination of the two, which is nearly constant. And here I did display both sides of the linear combination in orange and blue. So you can see that the orange graph, which is a different fund, but with the right weight chosen from the regression, it does track the blue one pretty closely, but there are differences. And so if you form now the difference between the blue and the orange, that the signal you get is shown on the left, on the right. So this is the signal over, again, one day. Time is in seconds. What you see is that this one is much more mean reverting than the Coca-Cola Pepsi example. So if you look at zero, it's going to cross zero many, many times during the day. It's really very frequent crossings from zero. So if you say change your position every time, for example, you hit minus 0.005 or plus 0.005, you're going to do, hundreds of trades during this particular day. Okay, so this is again an example of pairs trading signal. This is in fact used a lot. These funds, these exchange traded funds with similar components. So this is a well-known strategy. And now some remarks about the strategy, which will we used in other examples is that, well, in practice, you don't switch positions from long to short every time your signal crosses zero, because you can have a signal which fluctuates around zero. You just have a tiny fluctuation on zero. That's not very interesting for trading, because if you go 1 cent below zero, 1 cent above zero, well, every time you make 1 cent, I mean, unless you're doing a very high frequency trading, that may not be so interesting, although it's not clear. It may be interesting, but so we will see that tomorrow. We will look at high frequency asymptotics tomorrow. But so it makes sense that you introduce a threshold, and you only trade when you cross zero, but then you reach at least some threshold. You don't trade every time it touches zero, but you wait until it reaches a positive or negative threshold to change your position. So there's always a threshold delta, which can have different meanings. It can be a statistical significance if you are doing a statistical forecast, or it can be simply a cost of transaction if you have to pay a spread every time you go in and out of a position. Then obviously you will not trade unless your signal is above that spread. So there's a threshold delta, which we will use a lot. And so we will consider realistic strategy. We trade when we reach a threshold. So typically this kind of but threshold or transaction cost is very annoying when you analyze continuous time strategies. But in this case, we'll see that it is essential. And in fact, it simplifies a lot the analysis. Now, as you saw in these examples, these signals, if they are successfully constructed, they will oscillate around a constant level, zero or something else. So we can always normalize them to have mean zero. So in applications to pairs trading, they're modeled as stationary processes with mean zero and some standard deviation. 99% of the papers on pairs trading use the Ornstein-Uhlenbeck model, and we will come back to it on Wednesday. It's a very important model, though most of the applications have used the Ornstein-Uhlenbeck model, but not only. There are also applications where you model the signals as a fractional process. I will also come back to this tomorrow and Wednesday. So the only thing you need is to model this as a stationary process. You estimate the mean and standard deviation, other parameters if necessary, and then you use these models to forecast S, and then you construct the trading strategies based on that. So here in this simple examples that I gave, the trading strategy is basically based on the choice of a threshold. If you choose the threshold, then you know when to trade. And one common choice is to choose the trading threshold as a multiple of a stationary standard deviation of the signal. Let's call it sigma infinity. So it means that I only consider the deviation from zero significant if it's a multiple of the standard deviation. That makes perfect sense, in line with any confidence interval type criteria you might want to use. And in fact, if in most empirical papers on pairs trading, a common choice used is one standard deviation. We can use two standard deviations, whatever. So this is a common choice. And but there are other people who have tried to look at less ad hoc choice of these thresholds. For example, there's a book by Lung and Lee who on pairs trading. So they use a stochastic control approach. You say, well, if S is a Markov process, basically choosing this threshold is an optimal stopping problem. So what's the best threshold? When do I sell? When do I buy? That's an optimal stopping problem. So delta should not be just fixed at one standard deviation. I should solve an optimization problem to choose delta. And they arrive at they use the Ornstein-Uhlenbeck model, which is again the most popular model in these applications. And with Ornstein-Uhlenbeck, they arrive typically at levels of threshold which are around a half standard deviation. That's interesting. And again, I'll come back to this in the second part where we will look at the Markov case. But so this is just for you to know what is used in practice. So you construct the signal by regression, estimate the standard deviation, then you use the threshold, which is 1 or 1/2 standard deviation, something like that. Okay, now once you do that, what does the strategy look like? So that's where we're going to see that it's linked to excursions. Well, this strategy, so let's look at a one-sided strategy only. So the one-sided strategy works in the following way. I have a signal, let's say it starts from 0, or I wait until it hits 0, then I start my trade. And all I know is that this signal is likely to oscillate around 0. So when it goes away from 0, let's say it goes up, and when it reaches a certain level delta, I say, oh, this is not going to stay at this level delta. It's going to go back to 0 at some point. So I know it's going to go back. So I'm going to short the portfolio, which corresponds to the value of this signal. And I will wait for the signal to go back to 0. When it goes back to 0, then I unwind the portfolio. I sell it again. I close my position, and then I will have made delta, because I shorted delta, I unwind at 0, so I make the difference, which is delta. So that's the idea, that's all. So how does that work? Well, to define the portfolio, you just need to define these level crossing times. So here's some notation. So my signal is called S. I define two sequences of stopping times, tau 0, tau k plus, and theta k plus. So tau I plus is the first time after theta I minus 1 plus when the signal reaches delta from below. And then theta, the next theta plus, is the first time after this hitting time of delta where I reach 0. So that's it. And then you start again. Then you define tau 2 plus as the next time after this when I reach delta, and then I reach 0 and then. So I go from delta 0 to delta to 0 to delta, and I define this sequence of hitting times. Okay. And now, well, the strategy I described is very simply represented in terms of these hitting times. The portfolio I'm recommending to hold is this. It's called 5 plus. It's simply hold, minus, short this, short the portfolio, whose price corresponds to S, between, when you reach delta, you short, and then you hold it until you reach 0 again, and then you unwind. That's it. So it means that in the blue part of the trajectory, I hold nothing, and in the red part, I short the portfolio. That's it. So short when S exceeds delta, unwind the position when S reaches 0. That's it. I remember that S is like in the pairs trading, S is the difference between two stocks. So it's simply a portfolio long and short. So shorting it means taking the opposite weights. So there's no problem. And so you can see that this leads to one trade over each interval theta I plus 1. And this interval corresponds to what? It corresponds to S, the signal starting from 0, reaching delta and coming back to 0. So this is what we will call an excursion of S from 0 to delta and back to 0. So you can see that these, what we call excursions, they correspond to exactly the trade cycles of this strategy. So each excursion from 0 to delta to 0 leads to exactly one transaction. And so that's why we're going to introduce these excursions. Okay, so now to summarize, so what are we saying? Well, what we're saying is that the strategy is represented simply in terms of these indicators of these stopping intervals defined by certain level hitting times. And the number of trades you do between 0 and t, well, is exactly the number of these cycles, which you can represent as a counting process d delta, whose event times are exactly these hitting times. So you count the number of times you reach delta from below after having reached 0. So this is a very specific definition. So we will call each of these intervals a trade cycle because they correspond to exactly one trade. And it's split into, as we saw, it's split into this blue and red part. Oh, sorry, I need to take this call. Okay, so sorry for the pause. So as we said, each of these trade cycles is divided into a blue period where you don't hold anything and a red period during which you short. So I call these periods the waiting period and the holding period. Okay, and also you can easily compute the profit over each trade cycle. So the profit over each trade cycle will be, well, at the end of the trade cycle, you make delta, okay, because you sell, you short at delta, you sell at 0. So you make delta at the end of the cycle. And during this cycle, well, it depends on the value of the signal, the portfolio you short. So it's the value you shorted at minus the current value. So this is the mark-to-market loss or gain at any point in time t. Okay. So as you can see from these expressions, the profit or loss, the frequency of transactions, the duration of the holding period, the amplitude of the loss, etc., will be linked to the properties and the structure of these excursions of S, which exceed the level delta. So this is fairly obvious from this example. And so here I give the example of when the signal goes up to delta and then back to 0. But of course, you can do exactly the same thing for downward excursion. So I can define similar level hitting times, tau minus, theta minus. Again, I start from 0, and then tau I is the first time after theta I minus 1 when you reach the level minus delta from above. And then theta I is the first time after tau I where I reach 0 from below, and so on. So you can define exactly the same type of thing with the minus. It's actually, you apply the previous notation to the signal minus S. And then in this case, you will buy the portfolio or the asset when you reach minus delta from above, and then you keep it during the red period, and then you sell when you reach 0. Again, you make the difference delta. And so the portfolio in this case is what we denote here phi minus. It's holding during the red part and then doing nothing during the blue part. Okay, so that's for downward excursions. And of course, you can do both. There's no need to. They're not mutually exclusive. You can, in fact, that's what people do. In pairs trading, they take a position if the signal exits some interval around 0. So you take the long position if you go below, and then if you take short position if you go above. But you can do both at the same time because these intervals are mutually exclusive, because you cannot be at the same time above delta and below minus delta. So you can run these strategies in parallel. And so this is called usually a convergence trade. So it's just the sum of these two portfolios. And they're defined through these stopping times that I just showed you. Now, this is the simplest version, but of course, you can add various features to these strategies. For example, you can say, well, you know, you can do this, but if your loss exceeds a certain level M, then I cut your position, or you're fired, whatever. So this is called a stop loss. So you can add a stop loss and say, well, if if you short the portfolio then if S keeps increasing, then you lose money. So if you short it at the level delta and then it goes to delta plus M, you've lost M. So you say, well, I have a stop loss. If the loss reaches M, then you have to close your position. So I define this additional stopping time, which is the first time after tau k plus. When you reach the level delta plus M, instead of going back to zero, you go in the opposite direction. Well, if you reach delta plus M, then I stop your trade, and then you have to close your position. Okay, this is called the stop loss limit. And this gives you, again, you have a similar expression. It's a slight change of notation. Instead of having the indicator of tau theta, you have tau, and then you replace theta by theta infimum of kappa, so which is again a stopping time. So again, so you can introduce stop loss with little change in the structure. You always have these hitting times. And then you can have other variations instead of, so here in these examples, I'm either shorting one unit.
Rama, can I interrupt you? Because I think there is a question in the chat.
Yes. Oh, I don't see the chat, sorry.
I can say.
Yeah, I can see it now.
Okay.
Can we think of an example? Yeah, commodity markets. I mean, there's nothing specific to stocks. I mean, I'm going to show these examples from equities, but in fact, these are widely used in fixed income markets. Some of the most widely used pair trading strategies are for bonds. You know, you take, for example, a 29-year bond and 30-year bond. They have to be very similar. So the difference has to oscillate around zero. These are very widely used in fixed income markets. And in commodities markets, yes, you use commodities which are linked together for a structural reason. Yeah. So nothing specific to equities, exactly.
Maybe it's time for a short break.
Yeah.
10 minutes break, or if you finish this slide and we make the break as well.
Yeah. So it's exactly the right time because I finished this part. So just the last example I want to mention is that in these examples I gave, you short one unit or go long one unit. But of course, there's no reason to short one unit or long. You know, it's the general idea is that you go long in one side and short in one side, but you can choose to short more than one unit. And in fact, a very popular strategy is to do linear sizing. So what's linear sizing means that, in fact, the more the signal goes away from zero, the more you think there's opportunity for profit, because if you short it at 10, then it goes to zero, gain 10. If you short it at 100, then it goes back to zero, gain 100. So one strategy is to do linear sizing. So the size of your position is going to be, in fact, proportional to the signal. It can be linear or any other increasing function. And it's, again, it's zero when the signal is close to zero, but if it goes away, you can short more and more, or go long more and more if you're going below. So this linear sizing is used a lot. And then it leads to a quadratic gain profile because you integrate against S. So it can be also a function. It doesn't need to be one. Again, then you can write in a similar way the gain, and we will see that for all these strategies, the profit loss and the expressions of everything you want to compute in terms of these portfolios is linked to the frequency, duration, amplitude, and structure of the excursions of S from zero, which reach certain levels, plus or minus delta in the case of the simplest one, and possibly other levels involving stop loss if you include stop loss and exposure limits. Okay, so so these are the examples I want you to keep in mind, and this will motivate the next part after the break, where I will introduce formally this concept of delta excursion, and we will define properly what we mean by excursions and see how this can enable to analyze these strategies in a systematic and simple way. Okay, so let's take a break. Thank you.
Okay, 10 minutes break.
Let's go let's go into more detail about these excursions. Let me give some more precise definitions, and then we'll see how we can exploit these ideas that I gave you in the first part to systematically analyze these strategies. So what we saw from these examples is that actually none of these strategies trade at fixed time intervals. This, in fact, very few, if trading strategies trade at fixed time intervals. This is what you see in many textbook examples, but most trading strategies used in practice are of the type I just showed you. They trade when some trading signal does something. So, so it means that the correct way to look at the path of the signal is to look at it in terms of these level crossing times. And so that's what I'm going to do now. So here are, so it means that instead of splitting the signals or the price paths into fixed time intervals, as you do in econometrics, like daily or hourly or whatever fixed time interval, which is arbitrary because trades can happen in the middle of these time intervals, and also trades may not happen at each of these time intervals. You need to split the paths of your signals into through these level crossing times. And that's what we're going to do now. So here are some notations. We will call E the set of continuous paths, real valued. And we will call E0 the set of such paths starting from 0. Okay. So if we slice our paths into every time they reach 0, then each piece will start from 0. Each piece will be in a 0. And now we define for a continuous path. So in fact, everything I do here can be done for right continuous paths, so allowing for jumps. It just makes the notation much more complicated. So I will show you all the statements for continuous paths, but they can be done for right continuous paths. There's no fundamental, conceptual difficulty, but just that it makes the presentation much more tricky. So now let's call Tx of f. So f is such a path, and I call Tx of f the first hitting time of the level x. Okay, if it's a not continuous path, it will be the first exit time from minus infinity. So first time you go above x. But for a continuous path, it's the same. And that's the only notation I will use, in fact. You can also introduce the first hitting time after t, but I will stick to this one. And now we can define what we call an excursion from 0 to delta. So excursion from 0 to delta, it's path which starts from 0 and reaches delta in a finite time. And then you stop it when it reaches delta. Okay. So this is the notation, E0 delta. It's a path which starts from 0, and in a finite time, it reaches delta. The hitting time of delta is finite, and then by construction, I stop it at that time. So I stop it at delta. And we need also to define another operation. So we're going to basically slice up our paths into such excursions, and then to reconstruct the path from the excursion, we're going to paste them together. So what is this pasting operation? It's what we call a concatenation. So I take two paths u and v, I can paste them together at time t. What does it mean? It means I get a new path, which is u before this time t and v after time t. But v, both of these paths start from time 0, so I just need to translate v. So at time t, it starts from v0. So that's the concatenation operation. So I denoted plus t. It means that I paste them together at time capital T. And so now if you follow these notations, it means that now if I take u, which is an excursion from 0 to a, and v, which is an excursion from a to 0, and I paste them together at some time after which U has reached the level A, then I get a path. The concatenated path is again a path which is in E0. It starts from 0, reaches A, and then so it goes along U until it reaches A, and then it goes along V back to 0. So that's this is an operation we will use now. Okay, so now I'm ready to define what I call a delta excursion. So what we called an excursion from 0 to delta is just a path which goes from 0, reaches delta, and stays there. But that's only the first part of what we're interested in. So what we're interested in is identifying signals which go from 0 to delta and then go back from delta to 0. So that's what I'm going to call a delta excursion. It's a full cycle. It goes from 0 to delta and back to 0. So what does that mean? Well, it's exactly what we want. I will call a delta excursion a path which is composed of two parts: an excursion from 0 to delta, followed by an excursion from delta to 0. So we call this set of these delta excursions U delta. And what does that mean? It means that there is a path in, so excursion from 0 to delta, we call them E0 delta, and then I have V, an excursion from delta to 0, and I paste them together at, well, the first time when U reaches delta. So U goes from 0 to delta, and when it reaches delta, I start V, and V takes it back to 0. So it's exactly like the picture I showed you before. Now, this decomposition is unique because I do the pasting at the first time that U reaches delta. If U reaches delta and then stays there, well, I can start from the first time it reaches delta and go to 0, or I can wait and then go back to 0. Then it's not unique. But if I by convention, I say that the first time U reaches delta, that's when I start V, then there's only one way to do that. So this decomposition is unique. So we call the duration of the delta excursion the sum of the two durations of U and V. So the duration of U is, well, it's exactly the first the first hitting time of delta by U. That's when its lifetime ends. And then the duration of V is V goes from delta to 0. It's the first time V reaches 0. So I will call the duration of the delta excursion the sum of these two durations. Okay. And it's easy to see because all these things are defined through hitting times. So hitting times are measurable functionals of F. So the map, which takes F to this decomposition and gives you the duration, it's a measurable map. And this will be important afterwards when we apply this to stochastic processes, because if F is the stochastic process, sample path of a stochastic process, then all these things will be random variables. Okay, so what examples of delta excursions do we know? Well, simplest examples is this. If you take an excursion from 0 to 0, whose maximum is greater than delta, it means it's a path we're going from 0 to 0, which reaches delta at some point. Well, then that's an example of delta excursion, because you can always split it at the time when it reaches delta and then call the first part U, second part V. So that's an example of this decomposition. So we call these, I'll use this notation gamma delta in the next few slides. So obviously these excursions from 0 to 0 which reach delta are delta excursions, but as I will show you now, they're not all delta excursions. So U delta, the set of delta excursions, is much bigger than this because the way we define excursions from 0 to 0, E0, 0, is you stop at the first time you reach 0. But in a delta excursion, you don't need to stop at the first time you reach zero. You can reach zero infinitely many times, 10 times, whatever you want, until you reach delta. And then afterwards, you go back to zero once. But before you reach delta, you can go through zero many times. So that's allowed. And that's, so it's different from, it's not going to be a subset of excursions from 0 to 0. Any questions about these definitions before we go on? So the important thing here is that in the definition of excursion from 0 to delta, you stop at the first time you reach delta. That's very important. It's not any path from 0 which reaches delta. It's you only reach delta once and then you stop. So this it can only reach the destination once, and that's when you stop it. Okay, now this is so this remark I just made is I'm going to clarify it with the lemma. So as we said, examples of delta excursions are excursions from 0 to 0 which you reach delta. That's what we call gamma delta. But I claim that these are, and I said that these are not the only delta excursions, because these guys only reach 0 once. They go from 0 to delta and then delta to 0 exactly once. But there is no restriction for a delta excursion to reach 0 once. It can reach 0 many more times. So these are special delta excursions, the delta excursions which also reach 0 once. These are intersection of these two things. But these kind of delta excursions play a special role, and we will use this role later in the constructions we will do. It turns out that each delta excursion contains exactly one of these excursions of type gamma delta. So, and this is formulated in the following result. It's called the last exit decomposition. It's if people are familiar with excursion theory, may have seen this kind of thing. Last exit decomposition was extensively used, for example, by Markovian in his work on Brownian excursions. So this is a very useful concept. I just going to formulate, state this result here. We're going to use this a lot because it gives you nice correspondences between spaces of excursions. So the statement is the following, just what I suggest in words. It says that if you take any delta excursion, so remember, delta excursion is something which goes from 0 to delta and then back to 0. Then this is a path which goes from 0 to delta back to 0. It has a unique decomposition into the concatenation of two objects. First one is a path which goes from 0 to 0, which does not reach delta, followed by an excursion from 0 to 0, which reaches delta. So that's the statement. So this exact statement is this. For any delta excursion, you can write it as a concatenation of two objects at some intermediate time t. And the first object goes from 0 to 0, and it never reaches delta. The second object, which comes afterwards, it is this object called gamma is of type gamma delta. It's an excursion from 0 to 0, which does reach delta. Okay, and there's only one such decomposition, strangely. And this is called the last exit decomposition because, as I will show you now, the time t here involved in this construction is the last exit of f from 0. That's what I'm going to show you now. And here's a picture before I show you the proof. Here's a picture. So here is this entire path is a one delta excursion. Well, you start from 0, you oscillate, around 0. Delta is in this example is 1. Okay, so I oscillate around 0, and as you can see, I hit 0 many times, and here maybe maybe if I zoom in, I will see that I hit zero infinitely many times in the middle. It doesn't matter. I'm allowed to. Until I reach delta. I reach delta equals 1, this here. And then afterwards, well, the definition of delta excursion is that I have to stop the first time I reach 0 after I reach delta. So after I reach 1, I reach delta only, I reach 0 only once and I stop. So this entire path is one delta excursion with delta equals 1. And the last exit decomposition says the following: this path has a unique decomposition into a path G, which goes from 0 to 0, which never reaches 1. This is the violet part, this part. And then followed by a path which reaches delta and goes back to 0 exactly once. This is the orange part. So graphically, it's very clear how you do this. You start from the end, you go back. Okay, if you go back, at some point you reach delta, and then you go back from there, and the first time you reach 0 going backwards is the time t. And then what's before t is g. So the construction from the picture is easy. So you go backwards and you detect one delta excursion going backwards, and then you stop. And then what's left is the first part G. Okay. So, and that's why it's called last exit decomposition, because the point where you cut is exactly your last exit from 0. And this is exactly what we're going to do. So we take a delta excursion F. So what is delta excursion again? It's the concatenation of U and V, where U goes from 0 to delta and V goes from delta back to 0. And you concatenate them at the first time U reaches delta. Okay, so this is the definition. Now, and then afterwards, F is 0, so we don't care about what happens after the lifetime of V. So we only care about what happens before this lifetime. So now we define T as the last 0 of U before U reaches delta. We look at the first part. So this first part U has to reach delta at some point. And I look at the last time it visits 0 before reaching delta. Okay, so this is not a stopping time, obviously, but I don't care. I don't need it to be stopping time. And this is called the last exit from 0. Now, and then by definition now, because of the properties of U, before, well, this T is strictly before the hitting time of delta. And so the maximum of U before time T is strictly smaller than delta. So if I call G the function U restricted to the interval 0 capital T, this function never reaches delta by construction. So, and then I call gamma what's afterwards, then, well, then you have the, you have that G concatenated with gamma gives you back F, but now the first part never reaches delta and the second part reaches delta exactly once and reaches 0 exactly once. So that's a decomposition. So this last exit decomposition is useful because it will be useful for us to find the correspondence, a way to count the delta excursions and link them with the classical excursions from 0 to 0. At this point, it's not clear, but it will become clear when we look at the Ito theory. Anyway, so now, okay, let's forget this for a moment. So this is, I'm not going to use this last exit decomposition until Wednesday, but the interesting thing now is this. So we showed that these strategies correspond to trade cycles which occur exactly when we go from 0 to delta and delta to 0. So this is exactly what we call delta excursion. So it means that if we want to explore the properties of these trading strategies along a price path, we need to somehow decompose the price path or the signal path of the signal into delta excursions. Now, the following result that I'm going to show you now tells you that, well, you know what, that's nice because this is always possible. And you have a nice and clean way to decompose any signal into a concatenation of delta excursions. And this is the statement here. So any path, so here when I say path, I mean continuous path. But again, all of these results hold for Cadillac paths, but with the heavier notations and more indices. So any path has a unique decomposition into delta excursions. So the statement is this: if I take any continuous function starting from 0, but it doesn't need to start from 0, or I can just take away the first part. Then, well, it has a unique decomposition into delta excursions, which is explicit. And the decomposition is simply the following. I define these successive hitting times. So tau I plus is the first time I reach delta after theta I minus 1, and theta I is the first time I reach 0 after tau I, and so on. So I just will go from 0 to delta, delta to 0. Every time I call these hitting times tau I, theta I, and so on. Then, well, there are two statements here. First of all is that if I count the number of level crossing times theta I in any interval 0t, they're finite. So I can define a counting process d delta, which counts how many times I've cycled between 0 and delta on interval 0t. And this is finite. And then the path S can be decomposed in the following way. There exists excursions from 0 to delta, called UI, and excursions from delta to 0 that I call VI, such that I can write S in terms of this sequence of excursions. And this is exactly the concatenation of UI and VI that we defined. So each term here is exactly one delta excursion. And so this decomposition says, well, the number of delta excursions I need is d delta plus 1, where d delta is this counting process. And each of these delta excursions is defined in this way in terms of these hitting times. Okay, so this is the result. I'm going to show you where this comes from. The proof is fairly explicit. So, well, how do you show this decomposition exists? Well, you just do it explicitly. In fact, we already did it by showing the expression. You just define these level hitting times. I just defined them several times. And then you define U and V in this way. U is, you start U from when S reaches delta. Sorry, when S reaches B0, you start U, and then you run it until it reaches what we called theta I, and then that's when you hit delta. And then from that point on, you start V, and if you want to normalize V to start from 0, you add, you have to subtract delta here, and then you continue along the path S until you reach again 0. So that's all. So this gives you U, I, and VI, and then you just verify that by construction that's shown here. The increment of S is, you can decompose it into increment of U and increment of V. So this is a fairly simple decomposition. So this shows just that, you just check that the definition coincides with what you started from. And then why is this finite? Why is this number of hitting times finite? Well, because it's continuous, and in fact, it also will hold if it's Cadillac. So if S is continuous, then it's uniformly continuous. So you can show that if the number of these level crossing times is infinite, then you have a problem, because if you're on a finite interval, you go between 0 and delta infinitely many times, then well, you have a problem, because if you call these hitting times theta and tau, then you have that the infimum of these intervals has to be 0, but then yet you span a finite interval of length delta, so that doesn't work if it's uniformly continuous. So this shows that this process, this counting process, is always finite on any interval 0t. Okay, so that's all. Very, very simple. So this, so you can write this now in terms of a decomposition. So this, so okay, I showed you explicitly what the decomposition is, but you can also check that if you, so this is if you think of this decomposition into delta excursion as a map from the path S to some space of delta excursions, then you can check that it's a measurable map. So in fact, you're defining a measurable decomposition. And here is a different statement of the same thing in terms of maps on paths, which will be useful again when we apply to stochastic processes later. So this statement is more or less the same, but it says it considers now two cases. Well, what we showed is that d delta, the number of these delta excursions over a finite interval t, is finite for each t, but it doesn't say what happens when t goes to infinity. So there are two cases. So when t goes to infinity, when you consider longer and longer paths, either d delta can go to infinity or it can remain finite. Okay. So the first case is the one which is more interesting, probably because it corresponds to a recurrent path. So the path keeps going back and forth between 0 and delta. That's probably the case you're interested in. If you think you've identified a signal which is stationary, it means that it's going to go forever between 0 and delta. So this is the first case. If this is the case, then you have an infinite sequence of level crossing times between 0 and delta. And then the statement is that there exists a unique sequence of delta excursions, EK, such that I can write my signal as a concatenation of these delta excursions in order, E1, then E2, then E3, and so on. So that's the statement. The second case is, well, this is a non-recurrent case. It can, if I can have a signal which oscillates between 0 and delta, but at some point it stops. It sticks, it gets absorbed at 0 or doesn't go back to delta, whatever reason. Then the decomposition also works, but it's finite. If d delta stops at some integer d, then okay, well, there are decom components in the decomposition. There are d delta excursions, and then the last one is not a delta excursion because it doesn't go back either to 0 to delta. It stays in somewhere suspended in the middle, or it's just doesn't reach one of the 2 points. So the last one is just a path, but it's not a delta excursion. Okay, so that's also fine. So in all cases, there is such a unique decomposition. And in both cases, this decomposition is a measurable map of the path S. Okay. So this is just, I mean, the proof is, there's no extra proof, it's just the reformulation of the previous result. And now in terms of, I just distinguish these two cases. Okay, so the first case corresponds to the a recurrent path, which goes between delta and 0 infinitely many times. Okay. Any question about this? Okay, well, I can say, well, why are we doing this? Who cares about these decompositions, delta excursions? Why are you doing this? You started with trading strategies, now you show that it's bizarre things. Well, I'm going to end with this. So it's so in fact, I'm going to show you that this decomposition is exactly what you need to calculate various quantities of interest for these strategies. So in fact, I'm going to show you that the representation of the signal, which triggers all these traits, in terms of its delta excursions, this decomposition I showed you, leads to simple expressions, very easy to compute, for various path-dependent quantities, such as the profit or loss, the maximum loss, the drawdown of the trading strategies, in terms of this decomposition. If you give me the decomposition of the signal, I give you all these things and many more. So here are some quantities we're interested in. So we're going to go back to our trading strategy phi, any of the examples I showed you earlier. So obviously we want to know something about the portfolio value at time t, which I denote VBTF phi. The gain will be the change in the portfolio value between 0 and t, which in this case, because it's self-financing strategy, is also the integral of phi with respect to the value of the underlying portfolio S. Then we'll be also interested in the running maximum, the highest value it can reach, or it can be also the running minimum, the worst case loss, which is the same for minus phi. And then a quantity which is of interest for fund managers is the drawdown, is how much your value has dropped since the last highest value. So this is MT minus BT. So all these quantities are path-dependent quantities. So the usual approach is you model the prices via some stochastic process, which can be a Markov process or something simple. And then you want to compute these things. But even if it's a simple one-dimensional Markov process, typically running maximum drawdown, these are complicated things to compute. And the gain is a stochastic integral. It's not, but typically they're not very explicit things. But here, our point is that, and that's really justifies ex post all these that definitions, is that, well, if you give me the decomposition of the signal in delta excursions, then everything is easy. Everything becomes algebraic, finite number of algebraic computations. So here's the statement. If the signal S has decomposition, which is given by the previous theorem, so it's this is the decomposition of S into delta excursions, then the gain, the worst loss, and the drawdown of the strategy. So this is for the strategy I showed you in the first part. It's phi plus. It's the strategy where you short when you reach delta and then you unwind when you reach 0. But obviously you will have exactly similar formulas for the downside version and for the two-sided version. I'm just going to give you this one, but it's exactly the same type of formulas for all of the other examples. So what you see is that all of these quantities we're interested in have simple expressions in terms of this decomposition. So you give me this decomposition, I compute in 2 lines any of these formulas, any of these expressions. For example, what is the gain of the portfolio at time t? Well, it has this nice decomposition. I will comment on that later. It says, but you know, the gain of the portfolio at time t has 2 terms in it exactly. The first term is what we call the realized gain. Is you remember that every time I do a trade cycle, I go from 0 to delta and back to 0, I make exactly delta. Because I short at delta, I sell at 0. So I make exactly the difference. So the first term says it's if you have done d delta trade cycles, each time you make delta, well, the realized profit is delta times d delta. So this is very simple. If I just count the number of terms in the decomposition, I get the first term. And then the second term is telling me now I'm in the middle of the current trade cycle, which is the trade cycle d delta plus 1. And because I'm in the middle, well, I have shorted at delta, and then I'm somewhere, and the price is somewhere, which is described by the last component v of the decomposition. This tells me where I am. I started from delta and where I am. So this is my current gain. Okay, so this is the current market value of the portfolio. So this is the realized profit plus the current market value or the market value of the portfolio. So this decomposition has a very natural financial interpretation. And this is, in fact, how a fund manager would look at their decomposition. This is what I've made from the previous trade cycles. And this last term is what I have now in the mark-to-market value before I unwind my next portfolio. So this decomposition is what you would like from a financial point of view, but this is exactly what this decomposition gives you. So it shows that this delta excursion decomposition is very natural from the point of view of the fund manager, and it's exactly what they need. They don't care about the daily or hourly or fixed grid returns. They care about this because this corresponds to how they operate. Next thing, worst loss. Well, how do you compute the worst loss? Worst loss is a path-dependent quantity. Even if this is a Brownian motion, not very nice. How to compute? In this case, it's very easy. The worst loss, it's max over a continuum of times. But in fact, if I know this decomposition, it's a max over a discrete number of functions, which are exactly these the terms in the decomposition. I don't hold the position in the domain of UI. I only hold during VI. So I only need to look at VI. And if I know the maximum height of the excursion of VI, then it's going to give me the maximum loss during the excursion I. And since I started with a capital K plus 1 delta in the K excursion, because I've already made K excursions before, so I have the realized profit. I just need to look at the worst loss during excursion K and then take a max over K. So this is, I need to know basically the maximum height of these functions VI. That's all. Okay. Then what about the drawdown? Again, typically not easy to compute in most models or most examples. Here, it's very easy to compute again because I can break it down into the contribution of each excursion to the drawdown. And again, it involves computing the max of a finite number of functions. So again, what we see is that if I tell you even not the entire function, but just the heights, the maximum height of each of these excursions, that's in fact enough to compute most of these quantities. Okay, so I'm not going to go into the derivation of these. This is very simple. You can look at it in the paper, but the point is that the idea is the following. I start from the signal. So this is, for example, an example of such a signal. The delta in this case is, say, 0.5. First, I figure out the decomposition of the signal into delta excursions. In this case, it means decomposing this path into the blue and red points. How do I do this? Very easy. I just compute these hitting times, which correspond to subsequent crossings of delta and 0, and I color the U part blue and the V part red. So this is the decomposition. And then you plug this decomposition into the formulas on the previous slide, and I can compute the value of the portfolio, the drawdown, the worst loss, anything I want. But to get from the first curve into the following curves, I do not need to iterate through all the time steps or infinite number of times, but I do finite algebraic calculations. And in fact, it's even better. I do independent calculations on each part of the decomposition, and then I take a max. So if you want to do this in a code or do it in parallel, it's super easy. It's first you do the decomposition, then everything is done in one line for each calculation. So super easy. So that shows that this decomposition is not stupid. it seems to be very handy for calculating what used to be pretty complicated quantities. In particular, I would like to point out two things. First of all, the delta excursion of the decomposition of the signal leads to, I already commented on this, a natural decomposition of the portfolio gain into two terms. And I said that the first term can be interpreted as a realized profit. So what I've done in the previous trading cycles, how much gain I made from the previous trading cycles, that just gain per cycle, delta times number of cycles. And then the second term is the mark-to-market profit of my current position. So this has a non-natural financial interpretation, and the two terms depend on two different parts of the decomposition, and they can be calculated independently. Also, this decomposition enables me to define an effective trading frequency. Why? Because you see, unlike unnatural textbook definitions of discrete time trading, where you fix a grid and you say, I traded every time delta t, well, that doesn't work in this way in these strategies, because you fix delta, the threshold, and then, well, maybe if you cross the threshold 10 times, you trade 10 times. If you cross the threshold 1,000,000 times, you have to trade 1,000,000 times. So what's the effective trading frequency? Well, the trading frequency depends on the signal and your threshold, in fact. So the effective trading frequency is how many times you ended up trading per unit time. It's d delta t divided by t. And this depends on, well, the choice of delta, and especially on what S looks like. If S is a smooth function, you can imagine that the number of crossings will be well separated. So you will have a if you decrease delta to 0, you will not increase the effective trading frequency beyond a certain level, because you cannot cross delta more than a certain number of times if S is a smooth path. But if S has a rough texture, for example, if it's the path of a diffusion or some fractional bounding motion, then this effective trading frequency will depend strongly on delta and can do funny things. And we will see this tomorrow, that we can, in fact, analyze very in detail the effective trading frequency as a function of delta. And this is important because in these strategies, basically the most important choice is how do you choose delta. And we saw that in many cases, people choose delta as a multiple of standard deviation, but is that the right choice? Can you maximize your realized profit by choosing it smaller, larger, whatever? And in particular, many of these trading strategies are applied intraday. So theoretically, you could take very small deltas, and this would lead to very high frequencies. What's the correspondence between the threshold delta and the frequency? Well, this is the correspondence. The effective trading frequency is d delta divided by t. So can we compute this for various examples based on some assumption on S? And we will see, yes, we can compute this, and it's very interesting because it links to the local time properties of S. And we will see that this is, we can say many things about this. And in fact, it will lead to a quantitative connection between the trading frequency of these strategies and the choice of S. Now, I would like to note here that all the statements that I made today, I never really made any assumption on S, the signal or the prices. Are they stochastic processes or not? What properties they have in terms of stochastic processes? We don't need any assumption here. And tomorrow, I will not make any assumption either. I will show you tomorrow that without any stochastic, without any probabilistic assumption on the signal, we can derive many results which are pathwise. So it's just the property of the path, and which apply to a single path. And we can even do a high frequency analysis of these strategies without knowing what the underlying stochastic process is. So, but tomorrow, that's what we will do. And once we derive these pathwise results, then we will take examples of stochastic models, and we will apply the pathwise results to them. And in particular, what we'll do tomorrow is that we will not need to assume that S is a semi-martingale or anything of that sort. So the results we will apply to cases where S is a fractional process, something that can be statistically realistic for the signal you're trying to model, and that's fine because if they are strictly pathwise results. So that's what I will do tomorrow. I will I will try to derive some pathwise results for all the quantities that I showed you here, and again, but without making any probabilistic assumptions on S. So just to finish, so I showed you this formulas for the one-sided strategy where you short when the signal reaches delta and then you unwind when it reaches zero. Obviously, you can do the same for the downside by changing the signs. And but the decomposition I showed you is the decomposition of the path into one-sided delta excursions. So you can obtain a similar decomposition for delta smaller than zero. You just apply the above result to the path minus S. There's nothing special. And for two-sided, it's a little bit more subtle because, well, you can have minus delta excursions, so delta excursions and the negative side within a delta excursion. Okay, so you delta excursions, you go from zero to delta, then from delta to zero. In the second phase, you're above zero when you go from delta to zero. So obviously in the second phase, you cannot reach minus delta. But in the first phase, when you go from zero to delta, you can go to minus delta and come to delta. So the first phase can contain minus delta excursions. So it means that what you need to do is you first decompose into delta excursions. And then each delta excursion has two phases. The first phase can then be decomposed into minus delta excursions. So you can go from zero to minus delta, come back to zero, go to minus delta, come back to zero, then go to delta and so on. So you have to iterate these two operations. First, you decompose into delta excursions, then each delta excursion, the first component, you decompose into minus delta excursions, and then you concatenate everything back. And then you get the corresponding formulas for the two-sided strategy. So again, I'm not going to show it because it's too many indices involved, but it's straightforward, really. If you want to code it, for example, you just call one function and then you call the other function inside. So there's no problem really for this. And the only thing left is to show that the resulting decomposition is independent on the order. I mean, whether you first decompose into delta excursions, then into minus delta excursions, or the other way around, you will get the same thing. It's not very difficult to show. Okay, so that's just to, in case you were wondering about that. So I'm going to just conclude here this first lecture. So what did we try to show? Really simple things, really. First of all, I gave you some examples of very widely used dynamic trading strategies and showed you that all these strategies have a common structure. They're based on a signal, which is defined as the deviation of the market price of some portfolio from a target. So by construction, these signals oscillate around zero. They're supposed to be mean reverting around zero. And then I showed you that if you look at how these strategies trade, well, they trade, their transactions are determined by the excursions of the trading signal away from zero. More specifically, they trade when the signal hits some threshold delta or minus delta and so on. And so then we showed that, starting from this idea, we showed that, well, the relevant way to think of the signal is not in terms of maybe fixed time returns or some time series model or maybe even an SDE. We don't need infinitesimal descriptions or fixed time description. What we need is really a global description of the signal in terms of these delta excursions. If you give me the decomposition in terms of delta excursion, I give you anything you want. And then we showed that luckily this delta excursion decomposition is unique. It always exists. So if I get my hands on that, then everything is easy. I can compute all these path dependent things trivially, really. So now the next step is, well, okay, good. So can we actually use this in practice? Can we compute things from this? And can we do analysis of strategies? Can we compute the risk? Compute the high frequency asymptotics, compute the distribution of loss for these strategies when I make assumptions on S, which are, I know the process driving signal S, or I know something about the process, its roughness, and so on. And we will see that yes, yes, and yes, we can do all these things. And this will lead us to explore more the theory of excursion, which is really a beautiful chapter of stochastic analysis. And I will show a little bit of that tomorrow with pathwise results. And then on Wednesday and Thursday, we will look at the probabilistic results, which are based on Ito's theory of excursions. So I stop here for this lecture. If there are any questions.
Okay.